Welcome to the ECM students here in Oxford, and welcome to anybody who's watching, particularly from the International Centre for Climate Change and Development in Bangladesh and the Kwame Nkrumah University of Science and Technology in Ghana, and anybody else who's watching along as well. So the idea of this is that this and Yavinder's lecture on Thursday, which will be put out at the more Western Hemisphere friendly time of 2 to 4 in the afternoon. So that's not so good for Bangladesh, but we've got some collaborators over in, Yavinder has collaborators over in Peru who'd like to listen into that one. So these lectures are being broadcast, and there's the hashtag ECI Live should allow anybody who's watching along the lecture being broadcast to tweet in. So feel free to tweet in your comments, and Rachel, in fact, give everybody a wave, Rachel, so people know who they're tweeting to. Rachel, who's also your course animator for the climate course on the ECM, will be looking at those tweets and feeding them in to me as we go along. So we've got between now and 11 booked for this slot, but that's a long time for me to be talking continuously, and even longer for you to be listening to me continuously. So we will sort of, I'll lecture for a bit, then we'll sort of break for questions after I've finished one section, and then so there's basically 4 sections to the lecture, and we'll work through these sections as we go along. I'm going to be talking to you today, it's an overview of the climate issue, but since everybody's heard a great deal about the climate issue anyway, the particular angle I'm going to take is bringing you up to date on the latest findings of the Intergovernmental Panel on Climate Change, which is just finishing another cycle of its reports. We were having a bit of a flap with the projector before, and so I forgot to bring my copy in with me, but it's quite amusing to see. It's an enormous telephone directory of a report. The Intergovernmental Panel on Climate Change Scientific Assessment, which was released this time last year. And then there were 2 other assessments on the impacts of climate change and on mitigation strategies released about 6 months ago. And then next week I have to go back to one of these meetings where everybody stays up all night and argues over words to finalize the synthesis report, which will be released, we hope, if it gets agreed, at the end of October. So it's a good time to be looking at what the IPCC's findings are, highlighting some key findings from the IPCC. And that's what the main point of this lecture will be about. Since I'm talking to you, I can't, of course, resist talking a bit about what I think. And so climate scientists have to be a little bit careful on this score, because the Intergovernmental Panel on Climate Change's job is to provide governments with the science and the information they need to make decisions. It's not the IPCC's job to tell people what they think they should do. On the other hand, you know, we all have views, and so I'm very happy to tell people what I think about climate policy and what's important in climate policy, and I'm very happy to share those thoughts with you as well. But I'm sort of giving you a visual cue. When I'm going to material that's not gone into the IPCC because it's either too new or because it's my opinions, you'll see a slide that looks more like this. So see no IPCC branding on that slide, okay? And whereas if it's an IPCC looking slide, like this one, okay, with the IPCC's logo in the corner, that's stuff which has been peer-reviewed and assessed and looked at by a large number of scientists and experts around the world. Now, it's traditional when people start off talking about the IPCC to put up a slide like this one, which goes on about all the enormous numbers of authors and the numbers of reviewers' comments and the number of publications cited, sort of basically drowning you in numbers to try and stop you from arguing with the IPCC. And I actually think this is quite a misleading way to think about the science altogether, because science doesn't really work like that. Science is not a voting process. In the abstract of this talk, I promised to talk about some key numbers that matter and some key numbers that don't matter. So I would say, despite the fact that people talk about them a lot, about the enormous numbers of people involved in the IPCC process, I would say these are numbers that don't matter. Many of you may have heard, I don't know if you heard earlier this year, a study which got a lot of publicity. It was John Cook and co-workers, and they did a survey of climate scientists and came to the conclusion that 97% of climate scientists agreed with the consensus view on climate change. And this this paper was tweeted by Barack Obama, none other. And so it got a lot of publicity. Has anybody heard of this, heard of that 97% figure? So I actually thought that was a bit of a step backwards. Because, of course, immediately the conversation became, what method did they use to work out what fraction of scientists agreed? You know, is it 90%? Is it 94%? Is it, you know, there was a big, long argument about this. And that's the percentage of scientists that sign up to a statement is not a good indication of whether the statement is true. What matters is whether the statement is supported by the data and whether the studies which provide the basis of that statement are reproducible, whether other people who go back and look at the same data reach the same conclusions. And that's one of the things we'll find. So I'm going to take you through the actual evidence that the IPCC uses to support its statements so that you can see for yourself how the evidence works and why these IPCC authors came to their conclusions. In the end, you should become one of these authors, in effect. You can convince yourself of this. It's not that complicated. You don't have to take the IPCC's word for it. And in fact, I'll give you an example of how, if somebody is, if even some of the IPCC's strongest critics, do you want to come in if you're wanting to come in? Yep, come on in now. Okay, don't worry about it. Find a seat. And I'll show you an example of how even some of the IPCC's most strident critics, when they actually look at the numbers, they actually come back and find pretty much exactly the same conclusions as the IPCC. So this is one of the statements that does matter, and it contains a number, although you can't really tell just looking at the statement what the number is. So that's a quotation from the recent IPCC report. It's extremely likely that human influence has been the dominant cause of the observed warming since the 20th century. And this is basically a picture of the observed warming over the whole 20th century, but most of this warming's occurred in the second half. And as you can see, the warming we've seen so far over the whole globe has been slightly under a degree, but we've seen enhanced warming, particularly over continental regions. We've seen a lot of warming over Eurasia and Canada, up to almost 2 degrees already. Okay, that's warming since pre-industrial. So that's the pattern of warming we're seeing. This is just straight observations. And the number here, which I want to draw your attention to, is actually underlying that phrase extremely likely. Extremely likely has a formal definition in the IPCC process. It means we're 95% confident that climate change, that statement is true, that human influence is the dominant cause of the observed warming. This is a number that's has been slightly traumatic for me, because I had the dubious privilege of being live on the BBC. I don't know if they've recorded this, but I was live on the BBC while they were announcing the results. So we all knew what the results were going to be. Well, I knew what the results were going to be beforehand, and I briefed the presenter beforehand on what this statement meant. And but he just, I'm sure he knew what he was doing, and he just wanted to mess me around. So he got to this point. You know, the camera comes up, the red light goes on, so you know you're being broadcast. And he's turned around to me and said, right, so the scientists say they're 95% confident that most of the warming is due to human influence. What do the other 5% of scientists think? At which point I could have hit him, because that was exactly what I told him it didn't mean. Okay, but of course he wanted me to explain. No, that was. So that's what it doesn't mean. It doesn't mean that 95% of scientists think that. It means that scientists collectively, the authors of the IPCC, collectively believe there's only a 5% chance of them. The really formal way of saying it, there's only a 5% chance of us getting the data we've got, of us seeing what we see in the world, if that statement is false. That has lots of double negatives in that, but that's kind of how we do statistics. Okay? That's the level of confidence we have in this statement, which means we are that confident that we wouldn't see what we're seeing in the real world if that statement's not true. That's formally what it all means. Where does that confidence come from? Well, it doesn't come from just looking at the data. And the reason it doesn't come from just looking at the data is because the cause of the warming is not something you can go out and look at directly. You can go out and look at the temperature in Oxford, but you can go out and measure, well, you can go out and measure the temperature at a location. That's a direct observation. Even working out what the average temperature of the globe is, you can't measure that directly. You've got to infer it from a whole lot of different observations. And you've got to have some kind of model for how those observations relate to each other. So making any inference about just about anything to do with the climate system involves a combination of models and data, and this statement is no exception. We have observations of temperature in the black line here, and then we also have model simulations, climate model simulations, of how we would expect the world to have warmed if we include both human and natural factors, that's the red line here, or if we leave out human influence and just look at the response to natural factors alone, that's the blue line here. And as you can see in the models, if we look over the land, global land temperatures, we see there's a very good fit between the models and data throughout the series, and only if we include human influence. So if you leave out the human influence, you can't explain what's happened over the past 50 years. If you look over the oceans, there are more fluctuations away because oceans have more internal variability. You can see back at the beginning of the century we had a dip below the model expected line. In the middle of the century we had a dip above and so on, and right now we're having a small dip below. Oceans move slower than the land. They're sort of the sluggish part of the climate system, the lazy bit. Okay? It takes a while for the oceans to respond. So we're seeing more of this internal variability in the oceans, but if you look at the spread of climate model simulations shown by the orange band here, they haven't gone out of it yet. They're just dipping down a little bit below the center. But that period, this period here, the past 10 years, has caused a lot of excitement. People say, oh, global warming stopped in 1998. People like saying that, okay? And it's not strictly true, of course, but if you just look at surface temperatures over the oceans since 1998, you can draw a straight line through them if you work on it and get it to be close to horizontal. So what does that, what does this incident in the history of the planet actually tell us? And how do we work out from data like this how much of the warming is due to human influence? And I want to go through this in detail to explain to you how we actually do it. Because again, I think this seat's free as well if you want it. I think so, yeah. For those watching abroad, people always sort of rock in and out of Oxford lectures. It's just the way it works here. Okay, it's all pretty relaxed. Okay, so sorry, I'm just winding you up. That's fine. Okay, so the reason I want to go through this in detail is because lots of people think that the reason scientists say that most of the warming is due to human influence is just because that's what the models do. And that makes it sound like this statement is dependent on us having faith in climate models. And it's important that that's not true, because there's so many reasons why climate models might get the response wrong. There's many approximations in climate models. We'll spend a lot of time on this course talking about how climate models work and how they might get some things wrong. So if you were entirely reliant on climate models, if you had no observations, then you'd be, well, we collectively as a scientific community would be very reluctant to say that we were prepared to attribute most of the warming over the past 50 years to human influence. The crucial point is we don't just look at the models. We start with the data, and this is a sort of another presentation of exactly the same observations, but I've colored them in to make them look pretty and also so you can keep track of them. The warm ones are red and the cold ones are blue, okay? But each of those is just 1 year's observation of global temperature. And then if I take all of these climate model simulations and average them together, I get the orange line here. That's the response to human-induced warming. You can see what human influence is expected to have done is after this is probably just noise here. It just basically more or less flat, and then a fairly rapid warming over the past few decades. What the models tell us we should have expected from natural factors, that's the combination of solar variability and volcanic activity over the past century, is shown here by the blue line. Each of those big dips down is due to a large volcano going off. So we had Krakatoa back in the late 19th century, Agung in the 1960s, El Chichon and Pinatubo more recently. So these are the big spikes, downward cooling spikes due to volcanoes. Again, that's a model average. That's a model simulation of what the models thought the world should have done in response to these drivers. And if we add these two together, we get the black line, which is simply the response to the combination of human-induced warming and natural factors. And one thing you'll straight away notice is, the combination seems to be sticking out a bit at the top. That was, remember I drew your attention to the fact that the observations were a little bit at the low end of the model simulations at the end of the series? Well, that's the same thing you're seeing here. So, is that sticking out at the top? Does that tell us there's anything wrong with the models? What does it tell us about how much of the warming over the past 50 years we can attribute to human influence? Well, to answer that question, we take exactly the same data, but we plot it in a slightly different way. And this is why I'm going to ask you to sort of exercise your three-dimensional imagination here. So I'm replotting this data, not against time in the horizontal, but against the size of human-induced warming the models are predicting. Okay? I'm just using that as a different way. So now the orange line is just a straight line, because I'm plotting the human-induced warming against itself. If I plot x against x, I get a straight line. Yeah? Everybody can sort of see why that's the case. If I plot the natural warming cooling, I get another, I can still see the volcanoes, but they're sort of distorted a bit. It's almost like taking a log scale in the horizontal. Yeah? You can sort of vaguely see where I'm coming from here. It's just a different way of presenting the data. I haven't changed the data in any way. But what this allows me to do, if I plot the data like this, is to show you, first of all, there's a strong relationship between the observed warming and the model predicted human-induced warming. But secondly, if we plot it in 3 dimensions, I can plot human-induced warming in one direction and the model's natural warming and cooling in the other, so we can sort of move it around, okay? And you can see that there's a relationship between the observed warming and what the models predicted to be due to human influence in one direction and natural factors in the other. Anybody want to ask a question about what on earth I'm doing at this point? Yeah? Yeah, if you want to ask a question, we've got a mic, because we'd like the questions to, yeah? I'm not trying to put you off asking a question, so somebody who's brave and prepared to ask a question through a mic. Yeah, because this is kind of fundamental to this, to how we do this. Well, somebody said yes, they wanted to ask a question. Or if they lost interest when they discovered they needed to. I'm just asking you to talk into a mic, because then people can pick it up.
How exactly are you relating human-induced warming to the natural warming over here?
Okay, thank you. So the models have predicted, is that mic working, by the way? Great, okay, thank you. Yeah, no, that's fine. Apparently it worked. It wasn't for the benefit of people in the room, it was just that they're recording it. So we've got, for every year in the series, we have the value of the orange line, the value of the blue line, and the value of the observations. So each of these dots corresponds to a year. And we know what the models said the human-induced warming should have been in that year. We know what the models said should have been the natural warming or cooling in that year. So if I was able to turn this over, frustratingly I can't, because my graphics don't quite allow me to dive into the screen and do it. But actually you can, because if you go to a website which we've put up called climates.ox.ac.uk/detection, it'll be on the screen in a minute, you can actually play with this data yourself. You can dive into it and pull the points around. But the point is that every time a volcano goes off, it comes forwards towards negative natural warming and cooling. And as the world warms with human influence, it goes in this direction as the models increase their human-induced warming. So that's what defines where these dots are. And if we do this, we can sort of, again, see how we can turn this cloud around and rotate it and look for a plane that fits through all the points. And that's what we've done there. And this grey plane is the plane that formally minimizes the distance to the points. You see all these little pins sticking up and above and below the plane? That's the distance of the points from the plane. And by fitting that plane, we've found how much human-induced warming and how much natural warming and cooling is contributing to the observed changes. And all we've done is we've fitted, it's just like fitting a straight line to a scatter plot, but we've done it in 3 dimensions. That's all it is. It's the simplest thing you can do, really, in statistics. It's called linear regression. And we'll come across this later on in the course. And we work out our uncertainty in our estimate of how much human-induced and how much natural factors and so on by just varying the slope of this plane and looking to see how those little pins, the length of the little pins, changes. And you can see that you can't vary the slope of the plane very much without lots of the pins getting quite long, without the residual, that difference between your data and your fit, becoming improbably large. And this brings us back to that idea of a confidence interval. If I was to push the plane down to flat in the horizontal, I'd really stretch these pins out here. It'd be very unlikely for us to see what we've seen if the human-induced warming is 0. So the slope of this plane in any direction gives us an estimate of how much warming we can attribute to human factors and how much to natural factors. The first thing you need to notice is it does slope in both directions. It slopes up to the back right of the box. That means we need both human and natural factors to explain what's been observed. We can't explain it with one or the other and leave the other one out. More questions about the plane? People seeing more or less where I'm going here. We'll revisit this stuff, but I'm just trying to give you, and it's a little bit technical, but the point is here, I'm trying to tell you what we actually do to arrive at those statements, so you don't have to just take the IPCC scientist's word for it. Yeah. Yeah, you do, please.
If the models were wrong, is this still model dependent to any extent? Because the main question here is whether the models are all wrong and all made up.
Yes. Okay. So it's model dependent in the sense that we're relying on the models to give us the shape of those curves in the the shape of the orange curve you saw and the shape of that natural curve. But we're not relying on the models to give us the size of the response. So now, getting the shape of that response is pretty safe because we actually know when we emitted greenhouse gases. That's well documented. And we know when other forms of pollution were going up in the atmosphere. So again, that's all very well documented. We know exactly when the volcanoes went off. So that shape is quite safe. What is not safe is the size of the response. That's what we need to estimate from observations. We shouldn't just rely on models to tell us what size of warming to expect from human or natural factors. So I was talking about how the slope of this tells us that we need both factors. You can go even further than that. If this slope of this surface is 45 degrees, that tells you that the models have got the size of the response to human-induced drivers exactly right. You know, for 1 degree of warming expected by the models, we've seen 1 degree in the observations. And if this slope is also 45 degrees, for 1 degree of warming or cooling due to natural factors, we also would see 1 degree warming or cooling in the real world. Now, this slope is estimated from the data, so it's not exactly 1 in either direction. But it's almost 1 in the human direction. It's rather less than 1 in the natural direction. What that tells you is the models are responding too much to these natural factors, but they're getting the response to the human factors about right. And we can use that information to turn the data around and go back to our estimate of plotting the data against human-induced warming, but now, instead of this orange line being at 45 degrees, it's slightly less than 45 degrees. And that tells you that the models were overestimating the human-induced warming by a small fraction, and also, if you can remember, those spikes have shrunk. This is the most likely natural warming and cooling, and the spikes are slightly smaller than they were just coming out of the raw model simulations. And that's telling you that the best fit to the data, our best explanation of the data we have, is with a little bit less of a response to volcanoes than most of these models suggest. And we think we understand why this particular class of models over-respond to natural factors. Notice one other thing. That little problem at the end has now disappeared. Okay? We're now fitting the data at the end of the series. So if we go back to plotting against time, the sort of familiar way of presenting this data, we can then overplot this best fit combination, the best fit human-induced warming, and the best fit natural warming and cooling. And you can see again, we've got a good explanation of the data. And if we can look at the residuals now, that's the differences between these observed dots and this best explanation. If I plot those here, that's the red line, and I compare them to what we expect from lots of different simulations of climate models, you can see it's all pretty consistent. You know, the observations wobble up, they wobble down, but then that's what the models do as well. They're not wobbling outside the range of wobbles we expect from the models. So we have a consistent, coherent explanation of what's happened over the past century, which attributes most of the warming since 1950 to human influence on climate. That's the sequence of reasoning which brings us to that conclusion. So it's not a straw poll of scientists, it's not a reliance on models, it's this comparison of models with data that brings you to that conclusion. And those conclusions are sort of summarized in this figure, which shows the contributions of different factors to the observed warming, shown in black here, and that's the total anthropogenic warming, which you can see is estimated to be pretty much the same as the total observed warming, with a fairly small range of uncertainty on it, which is why we were able to say in the latest assessment that we were 95% confident that most of the warming observed over the past 50 years was attributable to human influence. And the crucial thing is, you wouldn't have needed a whole team of scientists to do that. Just one person doing that analysis, doing it carefully, reaches the same conclusion. That's the point I'm trying to drum home here, because this is how science works. If the world hadn't warmed up like that, we would not have reached that conclusion, no matter what the models had done, because it's dependent on this comparison of observations with models. This is a good point for questions.
So when you take in the greenhouse gases that you're actually predicting over there, that's more of based on the models, or that's more of what you've actually deduced from experimental analysis or from data?
Thanks. Yes, the greenhouse gas concentrations which drive these models, those come from observations over the past, since the 1950s, direct observations of atmospheric concentrations of carbon dioxide and other important greenhouse gases have been maintained. Before the 1950s, we're reliant on, when you go back to the 19th century, we're entirely reliant on analysis of air bubbles trapped in ice cores. But that's actually it's a very good source of information, because it literally is the air that was around then, and these gases are well mixed. So we actually have a very good estimates of how greenhouse gases have changed over the past century, and we use those to drive the models. Other forms of atmospheric pollution which also matter for climate, like aerosols, that's the pollution that's generated by, in particular, a biomass burning or sulfur-rich coal, then those are much less well quantified, and so we actually have to use a whole range of sources of information to try and work those out. But their history over time is quite well quantified, so and that's important. Even if we're not quite sure how big the aerosol forcing is at any one time, we do actually have quite good records of what pollution was like and how it changed over time. So again, we can get this shape of the response. We have more confidence in the shape of the response than we have in the size itself. So these are the sort of summaries of the sort of key observed changes of this part of the lecture. We see a very clear human influence on climate, and the recent pause in ocean surface warming, that's really the only place where we've seen any slowdown in the warming. Warming has continued at the ocean depths and has continued on land. It doesn't really change the big picture. This evidence doesn't depend on complex climate models. I was using, in that demonstration, I was using the average of all the available complex climate models just because they're there and a lot of people talk about them, so it was nice to show you the results based on that. But I could have done exactly the same demo with just my own very simple climate model. In fact, a very simple climate model I'll introduce you to in a minute, which we use in this course, which you can run yourselves. We give it to you on Excel. So it doesn't depend on these complex climate models. You get exactly the same conclusion no matter what model you use. And you don't need to take my word for it. Go and have a look at the data yourself. There's the website. And we've set it up such that you can play around with the data and judge for yourself how strong you think the evidence for human influence on climate is. And you know, this matters. Why does it matter? It sounds like a relatively academic question, you know, attributing warming to different causes over the past 50 years. You might say, well, it's warmed up, you know, that's what we care about. Why should we worry so much about exactly what's caused the warming? Well, there's two reasons. First of all, it helps us understanding the origins of climate changes today, and that's becoming increasingly important with the way international negotiations on climate change are going. And also it helps what we call constrain climate system properties. And those are going to be the topics I'm now going to focus on for the next little part of this lecture. So we're now going to talk about how we use this information we've got, this confidence we've got that most of the warming over the past 50 years is due to human influence, how we use that information to say useful things, both about what's happening now and about what's likely to expected to happen in the future. Okay, so I'm hoping you feel you've broadly got how we reach that conclusion about the fact that most of the warming over the past 50 years is due to human influence, because without that, nothing else really follows. And now we're going to build on that and talk about what some of the implications are. All right? So far, so good. So one of the core conclusions of the IPCC Working Group 2 report, that was the report on the impacts of climate change that came out in March of this year, was that in recent decades, changes in climate have caused impacts on both natural and human systems on all continents and across the oceans. And this is a schematic they designed which identifies impacts on human systems, shown in red, impacts on natural systems, shown in green, and impacts on the physical systems, shown in blue. So examples of these might be changes in glaciers in the Alps resulting from the warming, changes to human health in the UK. I think the studies they identified there, impacts of heat waves on human health, changes to marine ecosystems, all these fish, I think they're fish, correspond to marine ecosystems and so on. So the important message of this graphic is it's all over the world and it's everywhere. We're seeing the impacts of changes in climate on multiple systems, multiple sectors, multiple aspects of the global ecosystem. But notice here one thing, changes in climate. This statement doesn't say where those changes have come from. And that's something about the way the IPCC works, is that we have a lot of people working on the impacts of climate change and people working on the causes of climate change, and connecting those two up takes years, sometimes decades. So what this statement is about the observed changes in climate we've seen over the past 50 years affecting many parts of the world. But obviously there's still work to be done to connect those impacts back to the emissions that caused those large-scale, much of that large-scale warming in the first place. So this is what we can say on the basis of the literature available for impacts, but it doesn't necessarily connect every one of these impacts back through to human emissions of greenhouse gases. This actually illustrates another important constraint that the IPCC works under. The IPCC's job is not to present a view of climate scientists or even a particular group of climate scientists to the world. Its job is to assess the scientific literature. So if the papers aren't in the literature, it doesn't get said in the IPCC report. That's just the way it works. So at the moment, there isn't really a big enough literature tracing impacts all the way through from emissions for the Working Group 2 to actually make strong attribution statements for actual impacts all the way through to human emissions. So that's to some extent left to the reader, because you can see this is what the literature supports about the impacts of changes in climate. We have Working Group 1 saying that most of these large-scale changes in climate are due to human influence. You might conclude, right, that means that all of these impacts are due to human influence. that would probably be unwise, okay? Because we still have work to do. Many of them will be affected by human influence. I'm not writing that off, but we can't just assume that, because we've seen a role for human influence in the large-scale changes, and we're seeing a role for the large-scale changes in all these impacts. It doesn't necessarily connect the two directly. I just want to give you an example, though, and notice we've changed our logos here. So this is work done since the IPCC was finalized. The deadline, and that's inevitable that this was all work since the IPCC was finalized, because this was actually an event that happened after the sort of deadline for literature going into the IPCC. This was an extraordinary summer they had in Australia just 1.75 years ago. They had their December, January, February period was by far the hottest on record, and they had an extraordinary series of weather records, 123 weather records broken through Australia, and they in fact had one day, the 7th of January, where the average temperature of Australia was over 49 degrees. Did I get that right? It's in the abstract. Yeah. 40. Yeah, sorry. The hottest temperatures were 49, but the average temperature over Australia was over 40 degrees. That's more than your blood temperature. You couldn't survive even in a single location without protection or shade or something under that sort of temperature. And that was the average temperature over the whole country. It's quite an extraordinary statistic. And there's been a lot of interest in, as it happens, there was a major meeting of the Intergovernmental Panel on Climate Change in Hobart in the middle of this, which is, and so we were all there looking at and in fact this is a photograph taken by one of my colleagues, Peter Stott, at that meeting of the smoke from the wildfires in Tasmania that were going on at the time. Tasmania normally doesn't have wildfires. It's not a part of the world which is at risk from wildfire, but they had very severe fires that summer because of the dry and because of the heat. Now this illustrates what's going on here. So there's the hot summer. You'll notice, of course, they have had hot summers before, and but you'll notice there is a tendency for these hot summers to become more frequent as we go later in the series. And part of the process of understanding how human influence on climate plays a role in these kind of events is understanding how the risk of a hot summer is changing as the world warms. And this is actually a part of an aspect of science that we do a lot of work on here in Oxford, that we're also collaborating with colleagues in ICCC on, which is looking at how climate change is, if you like, loading the weather dice towards certain events happening and away from others. So if I showed you a handful of dice and threw them on the floor here, you'd sort of look at them and initially you think, well, that's just a bunch of dice. Okay? But hopefully, if you look at them long enough, you'll notice that you should be a little bit suspicious. Even if you haven't studied statistics, there are sort of slightly too many sixes on this. Okay, and if you work out I'll leave it with you as an exercise to work out the probability of getting that by chance, but it's pretty low. Okay, so what does this analogy tell us? Well, if we have a loaded dice and we roll it and we get a 6, did the loading cause the 6? Well, in one sense, no, because we might have got a 6 anyway. But in another sense, in quite an intuitive sense, yeah, sure it did. I mean, it made it more likely it was going to get a 6. And that's exactly how we need to understand the link between weather and climate. Did climate change cause Australia's hot summer? Well, if I can go back, they had a really hot summer in 1970. That was before this really rapid rise in global temperatures. Did climate change cause that one? Did climate change cause this one? Probably not. Okay? Did climate change cause this one? Well, in a sense, it didn't cause all of it. It didn't cause the fact that it was exceptional relative to the preceding summer, but it definitely loaded the dice in favor of a summer of that magnitude, of a heat of that magnitude occurring. And this is how we have to understand the link between climate change and extreme weather. And it's important that we do understand the link between climate change and extreme weather, because most of the impacts I showed you on that sort of pattern of impacts around the world, most of those impacts occur mediated by extreme weather. we actually don't see very many impacts of the slow change in background climate. Nobody even knows what the global mean temperature is, never mind being directly affected by it. What causes damage is extreme weather. Things like this record-breaking summer. That's some of the wildfires that were happening at the time. So, you've all got in your heads this idea of climate change loading the weather dice. One of the things you'll notice is that it took, I hope, well, I don't know, it depends how clever you are, of course. You've had to get through a very, I don't know how long it took you to realize that you were suspicious of these dice. But you probably had to look at it, well, I would have to look at it a couple of times. Oh, there's something wrong there, okay? Now, if the loading was very subtle, if there was only a little bit of loading, then you wouldn't be able to tell from this many dice. You'd have to roll it like hundreds of times in order to be able to tell that there's something slightly wrong with the dice. Yeah? So that illustrates a very important point, that we can't tell, just looking at sort of 1 or 2 summers, we can't tell immediately that some external driver has loaded the dice towards a particular event happening. We actually have to look at many, many realizations, many, many instances of the event we're interested in. And that, of course, is hard in the real world, because we only get to see the real world once. And the climate's changing all the time. So if we're talking about summers, you know, by the time you've detected a signal in warming summer temperatures, it's already happened. Climate change has already gone on. So the only way we have of doing this is actually using computer simulation, and this is something we do a lot of in this department, in this university, in climate science in general. And this is one experiment which has been focused particularly on this hot summer in Australia. We've been simulating using actually the public's home computers. So if any participants in the climateprediction.net project are watching, then thank you very much for all your computer time. And this illustrates what we're doing with that. What our colleagues in particular in Australia, David Caroli is the PI on this, and Mitchell Black and Suzanne Rosier are also working on this project, looking at lots and lots of simulations of Australian weather, the way it is now, and also the way it might have been if we hadn't raised greenhouse gas levels, if we hadn't interfered with the climate system. And they're comparing the two to see how human influence on climate has loaded the dice towards these extreme weather events. That sort of work which is ongoing. We have other work ongoing. Ruxana Rimi here is working on an experiment looking at South Asia. She's particularly interested in the Bangladesh region, looking at the role of extreme weather events in Bangladesh. But I'm going to tell you about, these are sort of results that are ongoing at the moment, but I'm going to tell you about an older event which was included in the IPCC report, so I can go back to my IPCC branded slides here, and for which we have analysed the role of human influence in this event quite carefully. This is also appropriate given my cycle ride home yesterday. Okay, it's not quite as bad as 2000, but it felt like it as I cycled home yesterday. Was anybody else here cycling? Did anybody else get totally soaked on the way home yesterday? Yeah, several people have put their hands up. Yeah, it was horrible. Okay, so this was the situation. This was obviously a nice sunny day, but immediately preceding it, we'd had a record-breaking season of rainfall, autumn rainfall in the UK in the autumn of 2000. And this event, it caused quite a lot of damage, and it also raised the whole question of, you know, what was the role of human influence on climate in weather events of this nature? And we published a study a couple of years ago which, for the first time, for an event of this nature, quantified how human influence had loaded the dice towards that event happening. And this sort of summarizes the results of that study. And it was based on many, many thousands of computer simulations of that season, of the autumn of 2000. Each one, they were all contributed by members of the public. So each one of these dots is some member of the public ran a computer simulation for us, sent us the results back, and we included it in on the these are all simulations we gave out. So we took a climate model, we asked people to do these simulations for us, members of the public then sent the results back, they were donating their computer time. And you can see the blue curve here shows how, as we go to less and less likely events, hydrologists like to use this notion of a return time. A return time of 10 years means there's a 10% chance of something happening every year. Yeah? It doesn't mean it will happen in 10 years' time, okay, because it's a random process, okay? But that's the jargon they use. So 10% chance of it happening, 1% chance of it happening, okay? So as we go to less and less likely events, the size of the event goes up. And the blue line here corresponds to the way the world is. That's with the present drivers of climate, the way, including the warming due to greenhouse gas emissions. Now, all this big fuzzy green area, that's many, many estimates of the way the world might have been if we hadn't caused this warming over the past 50 years, if we hadn't raised greenhouse gas emissions. And you can see that there's a general tendency for the green lines to be below the blue one. On average, that's a shift in this direction of around a factor of 2. So human influence on climate has increased the risk of a flood of this nature by around a factor of 2. Any questions about that figure? It's probably the most complicated figure I'm going to show you in this lecture, and we'll probably come back to figures of this nature if you want to know more about them. In fact, I'm sure we will, even if you don't want to know more about them, because I'm very excited about figures like this. But do people get the basic idea that we're using these lines to tell us how the risk of an event changes, how less likely events are bigger? Yeah, that's a sort of fairly obvious point. And in a world without human influence, we're seeing overall a certain size of event has become less likely in that world without human influence. Or to put it another way, human influence has shifted the lines to the left, making events of a given magnitude more likely to occur. Now, the reason I wanted to show you this figure is because some of the same group, and also working with our colleagues down at CEH in Wallingford, did a different study of a different kind of flood. So this is a flood that did happen in the autumn of 2000. This is a flood that didn't happen. And I'm really proud of the fact that we got this figure into the latest IPCC report, because it's a plot of a scientific study of a flood that didn't happen, which is right, this is really academic, okay? But it's important, because floods that don't happen, they have an economic impact just like floods that do. If you think about it, by not happening, they allowed stuff to go on that would have been damaged if they had happened, in a sort of, counterfactual way. Anyway, so the point is that this flood didn't happen, and it's a different type of flood. This is a spring flood, and we have in the past in the UK suffered from very severe flooding in the spring, resulting from a combination of accumulated snow and then rain on the snow. Snow melts very quickly and you get very rapid flooding. Now that sequence of events just doesn't happen anymore. Or at least it happens much more seldom. And so in this case, we've seen a decreased frequency of that kind of flood. So that's why it's very important to understand that not every extreme weather event that occurs is being made more likely by human influence on climate. But there's a science to be done to work out which is which. To work out which of the events are being made more likely by human influence and which are the ones that are being made less likely. Because only by understanding these things can we plan ahead. If we get an event like this one, we might still get it, by chance. Even if you've got a loaded dice, you can still occasionally roll a 1. But you wouldn't want to respond to that by saying, oh, we've got to build more defenses against this particular type of event because of climate change, because it might have just happened by chance. A couple of years ago, we had very heavy snow, two winters of heavy snow in Britain. And this caused a lot of excitement. Is this something to do with climate change? The general consensus at the moment, there was still some argument about it, is that it wasn't. It was just a fluke event. These things still happen. And therefore, on the basis of that understanding of these events, it wouldn't make sense to plan on more snow in Britain because of climate change. So you could waste a lot of money adapting to things that aren't happening if you react to every random weather event that occurs thinking it might be climate change. That's one reason why this sort of information is important. Of course, the other reason is that in the United Nations Framework Convention on Climate Change, there's an increasing interest in the whole question of loss and damage. What are we going to do about impacts of climate change that can't be avoided, that actually happen, that affect countries and particularly affect poor countries, and that result from past human influence on climate. And the reason there's a lot of interest in this is because it's widely recognized that most of the early impacts of climate change will affect countries that are not those that are primarily responsible for the problem. And indeed, well, Bangladesh, for example, is at the forefront of the argument that there should be some mechanism. There's a lot of argument about whether they can use the word compensation, but everybody kind of knows what is being talked about here. There should be some mechanism to recognize the fact that countries are being adversely affected by climate change. But if you want to quantify damage from climate change, you've got to be able to distinguish damage that's attributable to climate change, in the sense it's caused by weather events that have been made more likely by climate change, from stuff that just happens anyway. Because stuff has always happened. And unless you can make a distinction between the two, you can't provide a scientific basis for an assessment of loss and damage. So this, I certainly predict, will become a very important new science over the next decade as countries start to get serious about how they're being affected by climate change today. So that's how attribution science is being used in understanding what's happening now. And so far, I've been talking to you for 45 minutes, and I haven't mentioned the future once. Okay? And that's important. Okay? Because very often climate change starts in, people think of climate change starting in 2100. It's all about the far future. It's all about, scary things that might happen to our grandchildren. Well, this has been all about what's happening now. There's a lot we can say, there's a lot of important stuff, impactful stuff we can say about climate change without talking about the future at all. However, of course, this is an issue for the future. I'm not denying that. And so the next part of the lecture will be where we go on to talk about what all this means for the future. But this is also a good point to take a question or two if people want one. Any questions coming in via you? Yeah, sure.
Yeah, on the previous slide, the data points about the non-industrial period, I was wondering how these return times were calculated on the scale of millimeters per day, especially in this non-industrial period.
So it's a simulation, and that's crucial. You can't observe the non-industrial climate. In fact, we can't really observe 100-year weather risk directly in our present climate, because we don't have 100 years of stable climate to look at. So all of this is based on simulations using a weather model, but driven by the drivers that we know drive our actual weather. But of course, we use the same model for the two. So if there's an error in the model, it's going to be affecting the non-industrial climates as much as it's affecting the industrial climate. That's how we get these large numbers. There are other people who do this sort of assessment without using complex models, but they're still using models. So Geert-Jan van Oldenburg in the Netherlands uses statistical modeling to do the same kind of thing, but you still need a model. You can't observe 100-year risk directly. It's a bit like, how much of the warming is due to human influence. It's something you can only infer from a combination of observations and modeling. And the risk of a 100-year flood is also something you can only infer from a combination of observations and modeling. You can't just go out and look at it. Most of the things we deal with are like that. There's very few things we can just look at.
I was wondering on the same slide why there's more variation in the non-industrial modeling than in the blue line.
Because we know what the world's like today, but we're much less certain about what the world would have been like if we hadn't raised greenhouse gas levels.
Is the blue line based on observed data?
There are many, many different estimates of how much cooler the world would have been. Various other changes as well, but the big one is the global temperature change. How much, we're not sure how much cooler the world would have been if we hadn't raised greenhouse gas levels. So that's why there's many, many different green lines here, and they make this sort of fuzzy cloud. Whereas we do know what the temperature of the world is now, which is why the blue one is much more precise. Thanks. Okay, so on to the future. And the key climate system properties we're interested in, and you'll hear a lot more about these properties as we go through this course, are two. They're also numbers that these iconic numbers that people get very excited about, and I'll try and convince you that one of them that everybody gets extremely excited about and talk about a lot is actually not that important at all. That's something called the equilibrium climate sensitivity. There is another measure of how much the climate warms in response to rising greenhouse gas levels called the transient climate response, which is rather more important. And this schematic shows you what these two quantities mean. So if you imagine that you have a climate model, and in the model you ramp up carbon dioxide from pre-industrial concentrations around 280 parts per million, and you ramp it up exponentially at 1% per year. Over 70 years, you reach double pre-industrial, and then you hold it stable forever. Okay, so it's a simple, idealized experiment that you might do with a climate model. And if you took one of those complicated climate models I was showing you before, you'd see something very like this, except it would wobble up and down. Okay, but it would otherwise look very like this curve. This curve is smooth because it's done with a very simple model, which I can give you on an Excel spreadsheet. And in fact, I will give you on an Excel spreadsheet later on, or Rachel will give you on an Excel spreadsheet and tell you all about how to use it later on in the course. This model, although it's very simple, it's been fitted to the behavior of these more complex models, and it reproduces their behavior extremely well on long timescales. And it's actually provided by the IPCC. So for the first time in AR5, they actually give the simple climate model that they use for their calculations, which I think was a good innovation of IPCC. So it's very clear how calculations are done. And this is all one of the chapters in the IPCC report made a point of including in the supplementary information precisely the equations which they use for their simple modeling. And so I'm just running that. I'm still able to use the IPCC logo here because I'm running an official, IPCC stamped climate model here. So these are the two things we're talking about. As we ramp up the CO2, at the time we reach doubling, temperatures have reached a certain level. In this case, it's 1.5 degrees. And that's called the transient climate response. That's the warming we observe at the time of CO2 doubling after this 1% ramp. Okay? Now, the system's not in equilibrium at that time. It's been forced to warm up, and because of the oceans, and we'll spend some time in this course going through what's going on in the oceans over that, it then continues to warm for a long time, many, many centuries. In fact, the equilibrium temperature here wouldn't be reached until we'd run this for more than 1,000. We'll never actually reach it. We won't even get close to it until we've run on for getting on for 1,000 years. And that's actually the way these more complicated models behave as well. We have a rapid adjustment, and then we have a very, very slow adjustment, during which time, broadly speaking, the deep oceans are coming into equilibrium with the surface. That's what's going on during this period. And so, as you might imagine, because this takes such a long time to happen, and because we have observations of the system sort of around here, it's about 0.8 degrees, so we're about that sort of part of the process at the moment, we have very little information on what this equilibrium climate sensitivity is. So it might be up there or down there. These are sort of two values of equilibrium climate sensitivity. You can see it makes a difference in future centuries, but it makes very little difference to what we're observing when we're, during the ramp up, which is where we are at the moment.
So what were you changing there?
I'm changing the equilibrium climate sensitivity. Do you see here we are? There's the equilibrium climate sensitivity. It's 3.5. Here it is. It's 2.5. Two plausible values. Okay. The behavior of this little model is identical down here during the ramp up, but it's very different in the far future. Now, why does this matter? People agonize. They even go on big marches holding placards saying 350. Anybody here been on a march with holding a placard saying 350? I know Mark has. Okay. So because they're saying we have to stabilize concentrations of greenhouse gases at 350 parts per million. That's actually a very bad target, sorry Mark, because it's very difficult to say what would happen, say scientifically, what would happen if we stabilized carbon dioxide concentrations forever at any concentration. Okay? So it's the wrong thing to focus attention on. Why we're so fixated on this equilibrium response is a slight mystery. We could delve into that. It's kind of historical, but it's not if you were starting today, you wouldn't make that the focus of climate policy, because it's so difficult to say anything about the equilibrium climate sensitivity on the basis of things we can observe today. What we can say on the basis of things we can observe today is what the transient climate response is, because we're already halfway through that process. You can imagine we're sort of sitting here. We've seen how much warming is due to greenhouse gas increase to date, and you can't really change the transient climate response. Oops, hit the wrong clicker. You can't really change the transient climate response without changing the amount of warming we've seen so far. But you can change the equilibrium climate sensitivity. So if you want to keep an argument going in the blogosphere about climate change, mention equilibrium climate sensitivity, because then you can argue forever. It's like angels on the point of a pin. Okay? It's an indefinite argument, and everybody gets very passionate. There's no way of resolving it, and that argument will... the range of uncertainty of equilibrium climate sensitivity was estimated in 1979 to be 1.5 to 4.5 degrees. In 2007, the IPCC, with much fanfare, reduced the range of uncertainty to 2 to 4.5 degrees. Okay? And in the latest IPCC assessment, they pushed it back to 1.5 to 4.5 degrees, and everybody got very excited about that. Okay? Except those of us who think about these things and understand that nobody really cares what the value of this quantity is anyway. The number that does matter is the transient climate response, because that's what determines what happens in the future, and it also determines, crucially, what happens for a given amount of carbon we dump into the atmosphere. Now, this is where we ask, in order to sort of assess which is more important, the equilibrium climate sensitivity or the transient climate response, we have to ask, how would we get this constant CO2 concentration curve? What carbon emissions would we have to do? What would we have to do to stabilize concentrations at, say, 450 parts per million? Well, it turns out what we would have to do is reduce them a lot, but then keep them going, trickling out forever, in order to hold concentrations up at that nice constant level. Now, this is kind of totally implausible. We're talking, in real dates here, this is like 2200, and we've already reduced emissions by like 90%, but because we decided back in 2015 that we were going to stabilize concentrations at 450 parts per million, we've got to keep pumping out a bit of carbon in order to hold them there at 450. It's kind of crazy. This is not a scenario. This is not a relevant scenario for the future. We don't need to worry about the response of the system to indefinite stabilization, because we're not going to get indefinite stabilization. It's much more helpful to say, right, okay, what happens if we, at any given time, what happens if we stop emissions? And I know that stopping emissions sounds implausible, but I'll explain to you in a minute how the same logic applies to lots of different profiles of emission. So if we actually, instead of bringing emissions down suddenly and then bringing them down very slowly to hold them stable, we just stop them entirely. Okay? You see the only change there. That's all I've done. And now we see something interesting. Carbon dioxide concentrations come down very gradually from their peak. But look what happens to temperature. It just goes flat. And also, if I change the equilibrium climate sensitivity, it varies by less than 0.1 degree from its peak value. So if we can stop pumping CO2 into the atmosphere altogether, the system will never reach equilibrium for the foreseeable future, but temperatures will actually stabilize. And we'll have this slow decrease in CO2 concentration, and that corrects for this slow adjustment of the deep oceans, and we end up with a nice stable temperature. Well, it may not be nice, depends on what it is, but it'll be stable, okay? So, now this may seem a slightly arcane point, but the point is here that this peak temperature we get after injecting a certain amount of carbon into the atmosphere depends on the transient climate response. It doesn't depend on the equilibrium climate sensitivity. So if you want to know how much warming you get per ton of carbon you dump in the atmosphere, you need to know the transient climate response. You don't need to know the equilibrium climate sensitivity. Why does this matter? Because everybody agrees what the transient climate response is. Here's lots of different studies estimating the transient climate response. This is another figure from the IPCC. And apart from this one, and I think we, the authors of the chapter, sort of assessed all these studies, and we concluded that they were actually measuring something else, although they called it the transient climate response. So I think we can, and in fact the authors of that study agreed. We exchanged emails with them to make sure that they agreed with our assessment, and they said, yeah, okay, fine. So I think we can discount the yellow study there. All of the other studies agree what the transient climate response is. And very interestingly, a paper which came out quite recently by two authors who've been extremely critical of the IPCC. These are two authors who would definitely put themselves in the 3% on that 97% consensus paper. That's their estimate of the transient climate response, the 5 to 95% range. And you can see the point I was saying at the beginning, no matter who you are, no matter the political baggage you bring, if you go and look at the data, you end up with pretty much the same conclusion. On the numbers that matter. Yes, the estimates are all over the place for equilibrium climate sensitivity, but it's not a very interesting number in the first place. On the number that matters, on the transient climate response, everybody agrees, and all of these estimates are close to consistent with the range of responses of the current climate models. That's shown by the purple band there. Yes, questions?
I just want to ask you, what all attributes do you measure when you're measuring transient climate response and the equilibrium? Those two factors, what all attributes do you measure when calculating these two factors?
Sure. We'll go through this in much more detail as the lecture course goes on. Do you want to hang on to the, I mean, well, it's okay. Let's bring it up just in case we get feedback. The transient climate response is relatively easy to measure because we've already seen the response to a ramp increase in greenhouse gases. And it's a measure of the response to a ramp increase in greenhouse gases. So, in effect, the key number that determines the transient climate response is the amount of warming we attribute to the increase in greenhouse gases to date. This is why I was saying it was so important that we attributed, not just that we'd seen a warming, but we attributed that warming to human influence, to the rise in greenhouse gases and other forms of pollution that's occurred over the past 60 years. If we hadn't seen that warming, we would not have these estimates of the transient climate response. These estimates depend, well, we would still have that one because that's just based on models. But all of these others depend on the observations, the observed global temperature change as well. Now, equilibrium climate sensitivity, we've never seen the climate in equilibrium. It's actually never been in equilibrium, so that's not surprising. But I mean, so you can only infer the equilibrium climate sensitivity indirectly, and you're much more reliant on models, therefore, in that sort of balance between observations and modeling when you're trying to estimate something that's so far removed from anything you can directly observe. And that's why different methods you use for estimating the equilibrium climate sensitivity, and there's a whole list of them I could run through, they all give different answers. So you have to infer that equilibrium climate sensitivity much more indirectly than you can infer the transient climate response. But the main piece of information on the transient climate response is just the amount of warming we've had so far and the things which have driven it. Yeah, sure. Sorry, we need to keep remembering to.
And what's the simplest way in which the ECS is actually determined, even in the indirect methods that you adopt?
Okay, there's going to be a whole lecture on that later in the course, so I was hoping not to go into it all now, but thanks. I would say the simplest way is by looking at the energy budget of the recent period. You look at energy going into the system, where the energy is going, how much is being stored in the oceans, how much is going into warming things up, and how much is being radiated back out into space, and you work out from that what the equilibrium climate sensitivity is. But we're already falling into the trap of obsessing over a number that doesn't matter. I keep telling you, the one that matters is the one you can just go and look at, well, almost go and look at. It's the one which is essentially the warming response to the ramp increase in forcing so far. So, given that we've got good agreement on the transient climate response, what else can we say about it? And this brings us on to the last part of my lecture. One thing actually I did do before. This in case anybody's downloaded the PowerPoint, by the way, this one isn't in the distributed PowerPoint because I wanted to include this. I put this next slide in after my cycle home last night. there's a lot of debate. I'm showing you the 5 to 95% ranges here. There's still a lot of argument about where the most likely value is within those 5 to 95% ranges. And some of these are quite skewed and have their most likely value down towards one end. But I would argue for policy that if you have a skewed distribution, the most likely value or the best estimate isn't a very helpful thing to have. And just to illustrate that point, courtesy of Ian Ashpole, who's taking a historic weather observation now. I'll tell you a bit more about that in a minute. Here's a histogram of daily rainfall in Oxford in October. We have a weather record here taken at the Radcliffe Met Station going back to 1827. It's the longest daily weather record in the world. We're extremely proud of it. And as you can see, if you asked me beforehand, I could tell you on the basis of detailed climatological observations, my best estimate of rainfall in October, in a typical day in October, is less than 0.1 millimeters. That's a light drizzle for about half an hour or so. So you don't need to, when you move to Oxford, don't worry about a raincoat. Okay? Now, if I gave you that advice, you'd legitimately by now be pretty angry with me. Okay? So, what I'm telling you, well, this is just a nice illustration of how, when you have a strongly skewed distribution, the best estimate is not a very helpful thing to tell people. People need to know the range of uncertainty. And in fact, one of the features in particular of the Working Group 2 IPCC report is a much greater emphasis on what they call a risk framing of the climate issue, where they emphasize the range of outcomes that might happen rather than focusing on the best estimates of what they thought would happen in the light of the evidence they had so far. So we'll come back to that risk framing, I'm sure, a lot in the course of this course. This, by the way, is Ian Ashpole pouring out the rain from the rain gauge at the end of last winter, which smashed all the records since this period began in terms of the accumulated rainfall over the winter. So we just had our wettest winter ever. And of course, there's a great deal of interest in what was the role of climate change in that wet winter, but that is another lecture. Okay, so back to why transient climate response is important. Well, okay, so we've got a slug of carbon going into the atmosphere there, and we then stop emitting and temperatures go reasonably stable. Let's imagine we put that carbon in, same amount of carbon, but just distributed differently over time, okay? So I've just done a box here because it was easy. Notice what happens to peak temperatures. Nothing, okay? For a given amount of carbon dumped, notice what happens to peak emissions. They're down by a third. Oops. But peak temperatures don't change at all. Because what drives peak temperatures is cumulative emissions, not the size of the emission peak. So everybody's arguing about should we peak emissions, and they still are arguing, despite strident comments from the scientific community. They're still arguing about should we peak emissions at so many gigatons of carbon dioxide equivalent. That's not what matters. What matters is the total amount of particularly these long-lived greenhouse gases, carbon dioxide and nitrous oxide, that we emit overall, over the entire Anthropocene period, not what we emit in any particular year. And this is important because this has really profound implications for policy. Because
sorry, you only talked about 3 or 4 decades. You haven't taken it right out to 250 years.
Yes, but it would still work. I mean, if you can go out to 2200. I mean, basically, it's the accumulated emissions. Okay, emissions in 2500. Yes, you can muck around with the relationship by putting in emissions many centuries. Say, if you started sucking carbon dioxide out and then pumping it back in again, all sorts. You could mess around with the relationship. But if you're talking about what determines peak warming, it's the total amount of carbon we dump into the atmosphere over this Anthropocene period. Yes, sure. This particular plot is just talking about an idealized experiment. But I'm showing you that because you can do this yourselves with Excel really easily, and we'll give you the little model which does it. But we get exactly the same result. Okay, just to hammer the point for Mark's benefit, we get exactly the same result out of much more complicated models using much more complicated scenarios. And this is one of the key figures coming out of the latest IPCC report. And it's the basis of this conclusion: cumulative emissions of carbon dioxide largely determine global mean surface warming by the late 21st century. And it shows how temperatures go up as we add more and more carbon into the atmosphere. And the main point of this figure is there's a nice linear relationship between the total amount of carbon we dump into the atmosphere and the warming we get. And it doesn't make any difference whether we dump that carbon slowly. The blue line here corresponds to an emission scenario where we slow down emissions rapidly, and they've pretty much stopped by 2100. The red line corresponds to a scenario in which we carry on pumping carbon out pretty much as fast as we can. And you'll notice that obviously the warming continues in the red scenario, but the relationship between cumulative emissions and warming is the same, independent of the scenario. So this is a ridiculously simple scenario and a ridiculously simple model, okay, showing you get the same warming for those two profiles there. You can do it yourselves. You don't have to take my word for it. If you, Mark, would like to put any profile you like in there with the same area under the curve, you will get pretty much the same peak warming. This is an exercise. I can't remember when do we have that class? You can come along. And it's an exercise in the class to experiment with this and work out how you can break this relationship. And it's pretty hard to break. Yes, it can be broken if you do esoteric things over multi-millennial timescales, but essentially on the sort of decade to century timescales we're talking about, cumulative emissions is what determines peak warming. So for now you have to take my word for it, but you won't have to take my word for it for long, because you'll be able to establish this for yourselves. And the IPCC makes the same point using much, much more complicated models, making the point that if we look at the results of many, many different climate models, these are the average of all of the different available climate models they had for the latest assessments, we find this nice straight line relationship between warming and cumulative carbon emissions. And you'll notice there's two plumes here. The pink one is the total human-induced warming, which is higher than the warming due to carbon dioxide alone because of the role of other greenhouse gases, particularly methane, and later on a large contribution from HFCs as well into those scenarios. Yeah. Sorry, yes, the microphone.
So, given this linear relationship, would a conclusion from this graph be that feedback loops are not very important, such as the melting of permafrost, which adds more greenhouse gases, and a water vapor feedback?
In these models, we don't see runaway feedbacks like that. Now, that doesn't, of course, necessarily mean they won't happen, okay? But there's no evidence that we see a sort of acceleration as we move into the future. So, but the IPCC was careful and said they only really expect this relationship to hold for up to 2 trillion tons of carbon dumped in the atmosphere. Beyond that, up to 2.5, I think was the point. They said, you know, beyond 2 to 2.5 trillion tons, the units here are thousands of millions of tons of carbon. So these are billions of tons of carbon here, or that would be 2.5 trillion tons of carbon. So beyond that, who knows what feedbacks might happen. And I think once you've warmed the world up by 4 or 5 degrees, I think it's sort of bets are off. You know, we can't really predict how the system will respond. But over this, it's a little bit, it's probably wrong to call it moderate forcing regime, because I mean this is pretty high forcing, but over this regime all of the models behave reasonably linearly when you plot them up in this way. That's not, of course, a guarantee that the real world will do the same, but that's what the evidence points to at the moment. Other questions on this very important figure? Carsten.
Well, there might be an argument why people see this concept critical. So if you go back to this one slide showing that actually the temperature stabilizes, So if people look at that and then they think, actually, whenever you switch off the carbon emissions, we are still safe. So the point, people might argue this is a kind of, well, worrisome concept to policymakers, not to scientists, is that they might think, well, then let's just burn that crap, and so shall other people deal with the, well, decreasing emissions, whatever, and then we are still fine. So there might be some sort of danger.
That's, that's a familiar point which has been made to me many times, that this is potentially an unhelpful thing to say. It's not. We actually had a paper a couple of weeks ago with Dave Frame and Adrian Macy. Adrian was a former chair of the Kyoto Protocol, New Zealander, making the point that it's not the IPCC's job to be helpful. And indeed, the IPCC was criticized by Christina Figueres. She actually gave an interview shortly before the Warsaw COP last year, being quite critical of IPCC Working Group 1 for drawing attention to this relationship. And she said firmly, carbon budgets, the implication of this, of course, is there is a finite carbon budget. You know, there's a certain amount of carbon you can afford to dump in the atmosphere if you want to stay below 2 degrees. That's the direct implication of this plot. And Christina Figueres, who's the executive secretary of the United Nations Framework Convention on Climate Change, came out and gave an interview to The Guardian where she said firmly carbon budgets will play no role in the IPCC negotiation, in the UNFCCC negotiations. And I found that very depressing to read, because that's basically saying we don't care what the scientists say, we're just going to go ahead and do what we want. Okay? The whole point of this negotiation process is that it's informed by science. And yes, sometimes the science isn't necessarily helpful for every different way of framing the negotiations. And exactly, this problem is out there. As soon as we started publishing these papers, for example, China jumped up in the negotiations and said, right, let's just do the sums. Per head of population, everybody else has used their, well, I mean, the US, Europe, and so on, they've all used their quota, so now they have to pay us, and we can carry on emitting, you know. But then they did some more sums and worked out, actually by now, or at least quite soon, they run out too, so that they stopped talking about that. But India is excited about talking about this. So yes, it doesn't make the this sort of observation doesn't necessarily make the negotiations easier, but it doesn't help for negotiations to be about the wrong thing. So I think, you know, even if the negotiations get harder, we should make sure that they're actually about the right thing. And that's what that's the key point I draw from this. More comments?
It's just so I understand it properly. Does that mean that within a sort of a specific carbon budget, actually the shape of the curve could be determined by other factors? So say, for example, you know, if it's less of an economic shock, for example, to have a certain curve or certain shape to your within your budget, then you could do that rather than a kind of, is that
exactly? So you know, that might be a much, sorry, if I went up and came down again gently, that might be much easier to do, and that would be a much more sensible, might well be economically a much more sensible scenario, but the temperature response would be the same. So what I love about this is that climate scientists have spent so much time saying, oh, it's very complicated. Oh, it's more complicated than we thought. We hadn't thought of that. It makes it more complicated. For once, we're actually telling people it's simpler than we said it was before. Okay? This is a radical simplification of the problem. If you want to stop climate change, you've got to stop dumping CO2 into the atmosphere. It's really simple. And if you want to know how much climate change you're going to get, well, how much CO2 are you planning to dump in the atmosphere? And that question matters. By the way, this is where we are now. Okay? The reason that question matters, that's past emissions. Okay? Just around 500 billion tons of fossil carbon. That's what's down there in terms of estimated conventional reserves. So that's what's already on the books of oil companies, coal companies, and so forth around the world. They're planning to burn that stuff. That's factored into their share prices. Okay? And that's the unconventional reserves if we, you know, continue to exploit new technologies like fracking, People are talking about mining methane clathrates and other exotic forms of fossil carbon. There's plenty of fossil carbon down there to drive temperatures to whatever level you might care to contemplate, or even levels you might not care to contemplate. Do you want to pass the mic back?
If you're talking about carbon budgets, is there an agreement on what temperature would be a sustainable level of temperature rise?
Yes. Crucially, the international community has agreed to try and stabilize temperatures below 2 degrees. So what this picture tells us, very straightforwardly, is that all of that lot, if we're going to use it at all, has to be either sequestered, that means the carbon dioxide has to be captured at source and buried back underground or somehow disposed of, or recaptured, that's scrubbed out of the air again after it's been released, which some people say is possible, but it will undoubtedly be very expensive, if we're going to meet that 2-degree goal. So there you are. There's the carbon budget. It's a little bit fuzzy at the end, because we're not quite sure what the carbon budget is. But, you know, as far as policy is concerned, we're here. We've got to stop by the time we get to there. It's not that hard. Mark.
Sorry,
Mike, yes. Can we pass it forward, Castor?
Just the 2 degrees goal itself was criticised by David Victor and others in a paper in Nature last week. Are you going to come to that?
I'm not actually, although I actually think that paper was... so the 2-degree goal has been criticised for a number of reasons. David Victor's criticism was that it was too simple, and he wanted to replace it with a much more complicated set of targets, which would have had more or less the same effect if you actually delve into what he was actually proposing. So, but a bigger issue is, you know, are we asking too much of ourselves to try and limit warming to 2 degrees? Maybe we'll find that actually 2 degrees of warming is not so bad, and we'd be happy with 3 degrees. Okay? Now, that's an interesting line of argument. Interestingly, it's not an argument I hear very often, because nobody seems to really want to talk about it. Environmentalists don't particularly want to talk about what might happen beyond 2 degrees because they're quite pleased with the fact that we've got this 2-degree goal and we're trying to go for it. Many environmentalists argue we should be going for 1.5 degrees anyway, I mean, rather than 2 degrees. Interestingly, the IPCC's critics, the people who people like to call the sort of climate skeptic or climate denial brigade, they don't particularly want to talk about what temperature. I keep asking them what temperature would you be happy with, and I've never got an answer from any of these guys. Because, of course, they don't really want to say, I don't care, you know, I'm happy for my grandchildren to deal with a 4-degree world, because, you know, that it's very hard to argue that would not impose quite substantial risks on future generations. So, but I think the crucial argument why 2 degrees actually works is that, in fact, if you think about it, the measures we need to take to stabilize, the measures we need to take today to stabilize climate at 2 degrees are much the same as the measures we would need to take today if we want to stabilize climate at 3 degrees either. Because again, if you think about this cumulative carbon budget, that's our carbon budget for 2 degrees. Our carbon budget for 3 degrees would be only another 500 billion tons of carbon. We've got to get onto a downward path in emissions to get emissions to 0. If we want to limit cumulative emissions to 1 trillion tons, we'd have to reduce emissions on average from now on by about 2.5% per year. I had done that some earlier. I didn't just do that one in my head. But you can go and check it. If you want to limit the budget to 1 trillion tons, you have to reduce on average by about 2.5% per year from now on forever. If you want to limit the budget to 1.5 trillion tons, you have to reduce emissions on average from now on by, I think it's around 1%. I haven't done this one, but you can work it out. Okay? So, big deal. I mean, emissions are going up at 2% per year. So the difference in emissions going down at 1% per year or 2% per year, yeah, okay, once emissions are going down, we can start to argue about that. But in the meantime, yeah, it's kind of a moot point. So that would be my argument against those who say the 2-degree goal is unhelpful, is that actually it's helpful because it sets a budget, it sets a framework in which we're going to have to address the climate problem. And even if it turns out that a future generation decides, oh, this is kind of hard work, we're going to settle for 3 degrees anyway because it turns out the impacts aren't so bad, that should be their decision, not ours. And if we're going to take the actions we need to take today to actually allow future generations to make that decision, we need to be aiming for the 2-degree goal anyway. And of course, there's also the possibility the future generation might decide that even 2 degrees is unacceptably warm and that they want to get it down even further.
You're friends with a lot of climate skeptics. Do they accept
Friends is a different...
You've had coffee with David Rose?
I have had coffee with them, yes. I'm civilized. I try to be civilized. I try not to...
accept this relationship between the
Do they accept this relationship? Yes, they say they do. You have to be very good at compartmentalizing your mind, I think, if you're in that particular camp. Anyway, conscious of the story. Yeah, sorry.
So, quick question. So the 2 degrees, that's global? Right?
Global temperature,
Yeah.
yes.
What's the range?
Oh yeah. Well, I mean, if you remember that map, I mean, again, we'll come into we'll come on in the lectures to the details of what a 2-degree world will look like. And yes, it doesn't mean 2 degrees everywhere. And if you remember that map at the beginning, we've seen a global mean warming of 0.8 degrees so far, but already we've seen warming in mid-continental regions of over 2 degrees on average temperatures, and we've seen an increase in the risk of heat waves in mid-continental regions of a factor of 10 or more. So, you know, we're seeing, even in a 2-degree world, for example, the record-breaking summer that we saw in 2003 in Europe would, you know, if we're talking about large-scale average temperatures, that would become a normal summer. So, you know, we're talking about substantial changes in the weather, even in a 2-degree world. And that's why it's perfectly possible over the coming decades, people might actually decide that even a 2-degree world is unacceptable. Which is why we need to be thinking about designing climate policies to cope with the range of outcomes, which is why this sort of risk framing has become such an emphasis in the IPCC process.
Yeah, very short question.
Yeah, sure. We keep forgetting the mic. Are you picking up without the mic? No. Okay, so we do need to use the mic. Sorry.
As a follow-up to the previous question, does the 2 degrees relate to the average of land surface area or also including oceans? Because if it's both, then the land surface will even be hotter than the 2 degrees, right?
Actually, the 2-degree goal was agreed. I mean, it was agreed in one of these really fraught negotiation sessions at the UNFCCC, and it's been left a little bit vague. But yes, it refers to global temperature, not land temperature, so we would expect land temperatures to be substantially warmer than, on average, than 2 degrees in a world that's globally 2 degrees warmer, certainly at the time we reach that target temperature. Over the ensuing centuries, it might restabilize, but that's what we would expect. So certainly in certainly mid-continental regions, we'd expect quite a lot more than 2 degrees, maybe 3 or 4 degrees by that stage. So it's important to recognize that a 2-degree world is not no climate change. It's a pretty substantial climate change. It's more than double the climate change we've already observed so far. But it's what the world's governments have decided they're aiming for to stabilize it. And if you ask me as a sort of, okay, my personal view is it's a reasonable target, mostly because, not because I think that 2 degrees is a particularly sacrosanct number, because I think that the things we would need to do to meet a 2-degree goal are the things we need to do, almost regardless of what the eventual temperature we decide to settle on. So this is where so just to get on to the sort of final sort of few minutes of the talk, just to talk about the policy implications of this carbon budget. And
I do have one question.
Sure.
Do you know roughly what the average land temperature would be for a 2-degree global warming?
Off the top of my head, I'm not sure, but I think it's about double. So I think you would be, because I'm saying, no, sorry, the average land temperature, no, mid-continental average temperatures would be about double. Average land temperatures would be, just based on the pattern of warming we've seen so far, will be 30 to 40% higher. So they'd be getting on towards 3 degrees. But that's a number we're going to drill into in future lectures. But it's still, oh, maybe Carsten knows the answer. Here, have the mic.
Well, your numbers are certainly correct, so I would say the same. My point is that actually the problem is not the 2 degree or whether you want to see 3 degree on land, and so that's not the issue. And the issue is always the speed of change. So, and that's something that's certainly in the report that people talk about. So they point that this is the important thing to keep in mind, because if you tell people, well, 2 degrees more, I don't care. I would be happy to have 4 degrees more here in the UK. So point is really to stress how important it is to, well, to not do it too quickly, because otherwise you mess up your whole ecosystem, and that's probably what the ecosystem guys can tell you much more about.
We are concerned about rates of change. We have much less control over rates of change than we have over the eventual change. Through CO2, the rates of doing something about rates of climate change is actually a very different problem to the CO2 problem. By and large, CO2 accumulates in the system, so once if you're emitting at a certain level, that's causing a certain rate of change, and it's going to keep doing that. You'd have to, if you halve the rate of emission of CO2, then 10 or 20 years later you might see a substantial reduction in the rate of change, but that's a huge reduction. If you just reduce by 10%, you won't see much difference to the rate of change. So CO2 primarily determines peak warming, the long-term warming we get. Other factors mainly determine rates of change, and I accept the argument that we need to worry about rates of change. On the other hand, in any scenario where we meet the 2 degree goal, we don't see warming faster than 0.2 degrees per decade. Because if you just think about it, you've got to draw a curve which stops at 2 degrees. Okay? And given where we are now, it's very hard to draw a curve that does that. Yeah? I mean, it's just, it would be, you couldn't get the emissions scenario to do that. Okay? So it's very hard to get a curve that warms by faster than 0.2 degrees per decade and still meets the 2 degree goal. And by the way, 0.2 degrees per decade was what we saw between the 1990s and the 2000s. So arguably, we've already seen, if we're going to meet the 2 degree goal, we should have already seen the fastest rate of climate change ever. That makes me sound pretty optimistic. Okay? But you could argue we can't afford another pair of decades in which the world warms as fast as it did between the 1990s and 2000s. That said, of course, there is always variability in the system, and if you just pick on a 2-decade period, you will see warming and cooling due to internal variability, and that, by and large, is warming and cooling that the world's ecosystems have learnt to deal with. By the way, there'll be a very interesting seminar at 11:30 today by Clara Desser over in atmospheric physics, looking at the interaction between human-induced climate change and natural variability. Clara's done a lot of work on this, on the fact that internal fluctuations can mask or even amplify human-induced warming on multi-decade timescales. So she's giving a seminar at 11:30 in atmospheric physics, about 50 yards away. Sorry for those watching online, you won't be able to get to it. But do go to that seminar if you can. Can I just promise, Carsten, we will come back to rates of change, because it's another big topic. But I'm focusing here on what the governments have agreed to, which is to try to limit overall warming to 2 degrees, and that goal isn't with a timescale attached to it. It's just said they're gonna stop the warming going beyond 2 degrees. They're not saying 2 degrees by 2050 or 2 degrees by 2100. They're just saying 2 degrees. That's the peak. And the reason this matters is if you think about what you need to do to avoid more than 2 degrees of warming, it means that all of this carbon, this is real carbon down there, it belongs to somebody. Somebody out there wants to make some money by burning it. And the only way they can do that without causing dangerous climate change is for it to be either sequestered, captured at source and buried, or recaptured out of the atmosphere. You can't afford to leave that CO2 in the atmosphere. And this illustrates a really important policy point, and one which I think, I'm hoping, will get into the UNFCCC process, because it has really profound implications for policy priorities on climate change. The same policies that might affect the rate of greenhouse gas emissions in 2020 are not the policies that are needed to stop carbon dioxide emissions before we release more than 1 trillion tons. Different technologies matter if you're trying to get emissions down in the short term compared to the technologies you need to get emissions to zero in the long term. And this is illustrated beautifully in this figure, which also comes out of the Working Group 3 report. This is the third report on mitigation strategies. And these are IPCC numbers, this is my most controversial slide, but it basically is showing you, but it's still IPCC numbers I'm showing you here. It shows you how much extra it costs to meet the 2-degree goal. So these are lots of scenarios in which we more or less meet the 2-degree goal. The standard one is where you allow all technologies to join in. So you use all available technologies to reduce emissions, and that's 100%. So that's our standard baseline. It's not a baseline in the sense that the baseline is normally the one where you don't do anything. So this is our standard mitigation scenario. Okay? And then we ask, what would happen if we ban nuclear power the way some countries have done recently? Well, that actually only increases the cost of meeting the 2-degree goal by around 10%. If we limit the deployment of solar and wind, which is what lots of NIMBYs in the UK would like us to do, because they don't like windmills. I don't know why they don't like windmills. I think windmills are nice. But anyway, there we are. They don't like them, and so they want to limit their deployments. That would also increase the cost of meeting the 2-degree goal by around 2%. If we limit the deployment of bioenergy, that increases the cost by around 25 to 30%. Okay, not so bad. If we don't do carbon capture and storage, it more than doubles the cost of meeting the 2-degree goal. Why does this matter? Because nobody's doing carbon capture and storage at the moment. A few countries are sort of dithering about thinking about it. But it's the one technology that, of all on climate mitigation, which if anything you could say is going backwards at the moment. More projects in carbon capture and storage were cancelled last year than were initiated. It's the one thing we need to meet the 2-degree goal, and it's the one thing we're not doing.
It may not be technically feasible.
It's perfectly technically feasible. They're already doing it. So, Mark and I will no doubt have a long argument about this, but I'll be able to call time in a quarter of an hour's time. So let's just, look, branding, okay? I've moved off IPCC territory here, but doesn't mean it's not true, okay? But, so, first of all, cumulative carbon emissions determine, this is just simply a true statement. Cumulative carbon emissions determine the long-term warming, and there's far more carbon down there than we can afford to dump in the atmosphere if we're going to meet the 2-degree goal. Okay, that's just a fact. I didn't need to change the branding to say that. It's also, I hope, obvious to everybody that the policies you need to reduce emissions in the short term are not necessarily the same as the ones that you need to reduce emissions in the long term. Carbon capture and storage is an illustration of the kind of technology that is completely useless for reducing emissions in the short term. It's very expensive, takes decades to implement, and you have lots of protesting German Greens saying they don't want to have, I'm just mentioning this because we have I don't know if you're a protesting German Green, we certainly have a German Green in the room, and they've banned carbon capture and storage in Germany because the Greens got everybody frightened about CO2 being buried under their houses. Interestingly, they actually store the methane reserve, the natural gas reserve for Germany under Berlin, and nobody cares. And yet they're really worked up about the possibility that carbon dioxide, which actually is not poisonous, I mean a small amount of carbon dioxide doesn't do anybody, the carbon dioxide level in this room, while I've been lecturing, has probably gone up several percent just because you guys have been breathing, and we do have our exchange filters, but you know. So you know, a certain amount of carbon dioxide emission doesn't do anybody any harm at all. You know, if the methane reserve of Germany belched out in a hurry, it would be pretty ugly. But anyway, nobody cares about that because it's been there for a long time. It does illustrate the fact that if you're going to do something like this kind of disposal problem, you have to do it slowly. You have to show people that it works. And we've just had an illustration from Mark, somebody with no information at their disposals piping up and saying, yeah, but it won't work. It's like, well, he doesn't know that. Okay, and the people who do it have been doing it for decades. What they haven't been doing is doing it at the sort of scale they clearly need to do it to meet the 2-degree goal. And they're not going to do it at that sort of scale unless they're given the incentives to do so, which we can do today if we focus minds in the right direction. Carsten, the German Green. Yes, I will give you the microphone.
well, you're right with the green. The thing, or the question which is important here, which some people might ask is, so why is it actually that CCS is cheaper than saying, why not invest in green technology in the first place?
Because, crucially, if you want to limit cumulative emissions, you basically have to make a decision about what's done to that carbon there. And if you simply ban it, if you simply say to the citizens of India of the 2080s, you're not allowed to touch your coal, first of all, that's ethically and politically somewhat questionable, but never mind. Suppose you were able to do that. What are the economic implications? Well, what we find, analyzing these mitigation scenarios, is that you can do a certain amount, replacing fossil energy with other sources of energy. But eventually, carbon capture and storage is the technology of last resort. It's the one you do when you've done everything else. It means if you don't do it, the only mitigation option you have left is the one that India and China absolutely won't accept, which is just you don't grow as fast. You just don't do stuff. That's what's left. If you ban the CCS, if you look at what happens in these integrated assessment models, what happens if you ban the CCS is you just have lower growth. Everybody tightens their belts and is a little bit poorer. Now, we can have a long and interesting discussion about whether growth is good and whether a world in which we have slightly lower growth and so on might actually be more sustainable and so on. But there's a lot of governments out there that are just not interested in joining that discussion. And if that is the price of solving the climate problem, they're just not prepared to talk about it. And that's why CCS, that's why not doing CCS has such an enormous impact on the cost of meeting the 2-degree goal, because what happens if you don't do it is you actually have to contract the world economy in the future in order to meet your targets. That's why it's such a huge impact on the cost.
I think you're making a lot of wild assumptions there. I mean,
I'm telling you what happens in the IPCC scenarios. You can go and look at them.
Well, silly old IPCC. The point, I mean,
all right, yes, absolutely. Just because it's in an IPCC scenario doesn't mean it's true.
That's
absolutely
in that case. But I completely agree, obviously, that India will need growth, right? They've got 500 million people without access to electricity, so they will need growth for a very long time. I think the point that maybe Greens would advance is that if you bring solar and nuclear and other zero-carbon technologies down below the cost of coal, then the coal will be left in the ground. And leaving it in the ground is the alternative to burning it and capturing it.
Sure. If we can bring solar and nuclear, if we're confident we will bring the cost of solar and nuclear down below the cost of scraping coal off the mountains of New South Wales, which is around $3 a tonne, then sure, we can solve the problem. But I think it's a big risk to take, to say we're counting on getting costs of renewables down that low so that the world will simply abandon fossil fuels spontaneously. At the moment, the world's showing no inclination of abandoning fossil fuels. We are working, in fact, ever harder to find more and more exotic forms of fossil carbon to dig them up and burn them. So I find the argument that if we can just get these other things cheaper, we will simply stop doing this difficult. It's also interesting, it's not supported by history, because this is actually a later lecture, but if you look at what's happened in past occasions where we found an exhaustible resource, and even if there's a substitute available, if there's an industry built up that uses that exhaustible resource, they carry on exhausting it until it's exhausted. I mean, look at what happened to whaling in America in the 19th century. It was a completely uneconomic activity by the end of the 19th century, but they still carried on pulling out the whales because that's what they did. They were whalers. And you can bet your life that, you know, the oil companies are not just going to hang up their boots and go home. They'll cut their prices. They'll work out other uses of fossil. They'll work out other reasons for selling fossil carbon, because that's what they do. Well, okay, now we're well off IPCC territory, and but it's an interesting conversation, I hope. So anyway, and the crucial point here is that as we see over the next few years, impacts becoming more evident, as we see, you know, arguments about loss and damage due to climate change becoming more becoming clearer, becoming more concrete, as people are actually seeing changes in the weather which are affecting their everyday lives and which are being affected by large-scale changes in climate, we will see greater and greater demands for climate action. Crucially, it's got to be the right action, okay? We should be pushing the policies today that will actually solve the problem in the long term. And what frustrates me about Leonardo DiCaprio on the New York Climate March is you had all that energy there. Was anybody here there? You had all that energy in that march, all these people very keen to stop climate change, but it wasn't totally clear what they wanted. What was the positive thing they actually wanted? I didn't see a single placard in the footage of that saying, promote carbon capture and sequestration. You know, it's like it doesn't make much of a placard, but it's actually what we need to do. Because if Mark's right and it doesn't work, then we've got a problem, because that means meeting the 2-degree goal is going to be twice as expensive as we thought it was going to be. So we better find out now if he's right. Just saying, ooh, it might not work, it's a bit like saying, ooh, there might not be oil there. It's the same kind of argument, you know. So, you know, you've got to go look for it, find out. And we've got to get the industry deploying it so as to find out if they can do it. They say they can do it. Let them put their money where their mouth is. Again, the UN climate talks, they're still fixated on short-term targets. They're fixated on what's going to happen in the next 10 years. They're not talking about the kind of targets they need, the kind of objectives they need to actually solve the problem in the long term. Interestingly, the world's largest carbon burial project at the moment is being built in the Gorgon gas field in Western Australia. At the moment, it's still being built, despite recent political developments in Australia, but I think it's going to be worth watching that very carefully. So we'll keep our fingers crossed that stays on track. And we have here in the UK plans to build a carbon capture and storage plant in Peterhead in Scotland. Unfortunately, this requires £1 billion of taxpayer investment, and like many £1 billion investments, it's been carefully parked until after the next election. But it's going to take, I'm certainly hoping, of course, that this goes ahead, because I think the UK was the first to get going on this spewing carbon into the atmosphere enterprise. We should be the first to really get going on putting it back where it belongs. So it would be entirely fitting for the UK to make a big investment in this area. And I've just got to hope that that survives the likely painful cuts that will happen after the next election, when they can implement them without the risk of being de-elected for another few years. Anyway, but that's just bringing it all back to the sort of rather parochial British climate politics regime. But that's given you an overview of the whole topic, and I hope it's given you a flavour of what we're going to be covering in the rest of this lecture series. So we were asked by Tom to give you, I think Tom called these overture lectures. So it's the idea of the overture, I think, is that you have each theme is sort of brought out, and you have a little sort of, you know, snippet of each theme. So that's what you've had. You've had sort of snippets of what we're going to cover. Don't panic if you don't feel you've absorbed it all, because we're going to be going back to all of these topics as we go on through the course. But I hope that's given you a broad brush view of the kind of material we're going to want to get through. Thank you. And thank you very much for anybody watching online.